That's just the recording starting. Okay, so I think we are ready to move on or move. We'll continue looking at functions and graphs. Today we're going to look at shifting, reflecting, and stretching graphs. And there are certain graphs we are going to look at which are called parent functions. So what we're going to want to be able to do today is recognize graphs of parent functions, and that's the first thing we're going to talk about here in just a second. Use vertical and horizontal shifts and reflections to graph functions, and use some non-rigid transformations to graph functions. So, like I said, the first thing we're going to talk about is some parent functions. And if you look here, we'll add a few more as we go, but whoa, that didn't work the way I wanted it to. Here we go. All right, so the parent functions we're talking about here are some of these right here. Now, just a regular linear function. The parent function is the simplest, and what the parent function is, it's the simplest form of the equation that forms a graph of what we're looking for. So the simplest equation that forms a line that's not horizontal or vertical is f of x equals x, which is that line right there that crosses through the center, has a slope of up 1 over 1. Okay. Then we have the absolute value function, which is f of x equals the absolute value of x, which forms a v. All right, with the vertex right there at 0, 0. The square the square root function, you'll see over here on the left, f of x equals the square root of x. It forms this sort of curve that starts at 0, 0 and sort of hooks up to the right. It kind of looks like half a parabola, in which is what it is. A half a parabola on its side is basically what it is. But remember, we can't include the full parabola because then it would no longer be a function. Quadratic function, the simplest one is just f of x equals x squared. That's a parabola with its vertex right there at 0, 0. Two more functions we're going to look at. The cubic function. F of x equals x cubed is this little sort of S-shape something that's increasing the entire time, that the center of it, sort of that reflection point, is at 0, 0. And then a rational function, which we won't talk about a lot today, but f of x equals 1 over x forms a graph that looks sort of like that, where you've got the y-axis is sort of a breaking point. It doesn't touch the y-axis. It sort of fits in between, both of those fit in between the x and y-axis. But everything we look at today is going to be somehow based around these. And basically what we're going to do is we're going to say, look at the parent function, like say the quadratic. And if we add a number to that, how does that affect it? Does it shift it up? Does it shift it to the right? Does it shift it left? Whatever. If we multiply, does it shrink it or grow it? If I use a negative, what does that do? So that's sort of what we're going to be doing. And all of these are listed in, if you look at your e-text for 1.3, that's where I pulled this right out of that the book. So you can pull up your e-text through WebAssign and look at these further if you need to. Let me shrink this down a little bit. So, all right. So let's go to the next slide. So we're going to talk about some of that again in this, but one of the goals is to enable you to build your intuition for the basic shapes of the graphs of different types of functions. So what we're basically saying is we want you to learn these parent functions so that if you look at an equation, you have an idea right off the top of the bat of what the graph should look like. So we can look at this, f of x equals x. We need to be able to determine the basic shape. We need to understand that's just a line, right? Y equals x, or f of x equals x. I know that my final answer is going to be some sort of line. That is a linear equation. So it is helpful to be able to recognize that. Okay, so let's talk about how it actually shifts the graphs. Okay. All right, many functions have graphs that are simple transformations of the graphs of parent functions. For example, you can obtain the graph of h of x equals x squared plus 2 by shifting the graph f of x equals x squared 2 units upward. So one thing we can do to show that is I could go ahead and pull up my calculator, and let's say I just look at the graphs, and that's nice about this one, it's got different colors. So I've got x squared. Okay, so that is just a quadratic. That's going to give me just a normal parabola. So what happens when I add 2 to that? Oh, I got to click it on there. So it's going to be x squared plus 2. And you can see what happens. It shifts it up. So this is something that's going to stay true to all these parent functions, is that if we have the parent function and we simply add a number to it, it shifts. Adding a number actually shifts that vertex, or shifts every point on that graph up 2 units. So we can guess as to what would happen if I subtracted 2. If I had x squared minus 2, well, your mind should go, well, if I added 2, it shifted it up 2 units from the parent function. Notice the parent function's in blue there in the center. If I subtracted 2 from it, it shifted everything down 2. If I had subtracted 5, it would have subtracted 5. It would have moved everything down 5 units. So it's a way we can get a quick graph, or have a quick idea of what this graph looks like, if we understand that adding a number to it will shift it up or down if you're adding or subtracting. Okay, so that's all that's saying right there. Now, notice how they wrote it here. F of x plus 2. F of x is equal to x squared. That's where we started. Our parent function was f of x equals x squared. All right, so basically, if we add a number to the function value, that's going to cause everything to shift up. If we subtract, it's going to cause everything to shift down. Okay. Now, vertical and horizontal shifts. Now, notice the difference. So a minute ago, we had f of x equals x squared, and then we took and added 2 to it, and that caused it to shift up 2 units. Everything on the graph to shift up 2 units. Well, notice the difference here. Here, we're not subtracting, or we're not adding 2, or in this case, subtracting 2 from the entire function. Like right there, we took the entire function that we started with, and we just added 2 units from it. Here, if we are starting with f of x equals x squared, notice what we did is we subtracted 2 from the variable x before we squared it. So what we actually did is we subtracted a number. Basically what we did is we are finding f of x minus 2 is basically what we're finding there. And this is what's going to cause it to shift left or right. So if we go back to our calculator, and let me get rid of the second 2, clear and clear. So if I put in parentheses x minus 2, and then I square it, all right, notice what happens. That actually shifts the graph to the right 2 units. Now, here's what you need to notice. minute ago when it was moving up, when I added 2, it moved it up the graph, which is a positive movement up the graph. Down the graph was a negative movement. When I subtracted, it moved it down. Here, it sort of works, if you look at it, kind of opposite. I subtracted 2 from the variable x, all right, and it caused a shift to the right 2, which is a positive movement. Okay, so we should be able to figure out if I change this, and I'm going to change it to, what if I do x minus or x plus 4 squared? All right. So minus 2 shifted it to the right 2. You ought to be able to determine what's going to happen here is when I add 4, that's actually going to shift it to the left in a negative direction. So the side-to-side movements sort of work opposite of how you would think. And notice that's what happens. When I added 4 to the x value, it shifted it back to the left 4 units. Okay? And that's what it's showing right there. Okay? So sort of same thing. All right, so that's what I was saying a minute ago. Basically, when the function, what the x value is, you're subtracting and are adding to only the x value, that's when it's going to cause it to shift left or right. And here is sort of the little chart that explains this right here. So notice if we take and add a constant to the function value, that's going to shift it up. We subtract a value from the function value, that's going to move it down. If we subtract a value from the x, only the x, not the entire function, that's going to move it to the right. If I add a value to the x, that's going to move it to the left. All right. So what we can do is look at what would happen if we had multiple shifts. If I had a parent function, and let's just say instead of using x squared, we use the absolute value of x. So let's say our parent function f of x equals the absolute value of x. Okay, and if I look at that graph, let me clear all these out. Let's look at that parent function. Remember, absolute value is math. I hit the math and arrow over one time, absolute value is right there. And if I take the absolute value of x and look at the graph, it is just that V graph. Okay. But what I do to the parent function is going to treat it exactly the same, just like I did on the quadratic. All right. So what if I say x minus 2 minus 4? Okay. How is that graph going to shift? And all we're talking about is left and right shift. So is this graph, is the x minus 2 minus 4, is this graph going to be shifted up or down from the original parent graph? Down, right here. This part right here is what's determining what shifts it up or down, right? I'm taking the original function and I'm adding or subtracting 4 from the original function. So this is going to cause it to go down. This part is going to cause it to go down 4 units. Now, inside the absolute value right here, this part right here, all right, that's like I'm taking and subtracting 2 from x. What's that going to do? Is that going to shift it left, right, up, or down? It's going to shift it right, correct? So this one tells us it's going to go right 2. So if I wanted to do a quick graph of this, my vertex is going to be down 4 and over 2, which that means it's going to be right here. And then that V is going to look something like that right there, right? I can get a quick graph of that if I wanted to go back to the calculator. And these calculators help us out so much because we can actually look at the graph. So if I have the absolute value of x minus 2, and then go outside and minus 4, we can see that's exactly what happens. All right. So that's not really too difficult to understand on what's causing things to shift left or right, up or down. All right, and this chart's also in that e-text if you want to look at it there. All right. All right, so quickly let's go through these right here and just describe what's going to happen. So all of these are based on the cubic x to the third power. And let's just state what's going to happen. So if I have x cubed minus 1, how is that graph going to shift from the parent? Up, down, left, or right? Down 1, right? That one shifts down 1. This one, with the x minus 1 on the inside before it is cubed, is going to shift right 1. And then this one is going to be a diagonal shift. It's going to shift up 1 and left 2. Very good. Not very difficult at all. All right. And then they just show, there's that graph. We can look at it here if we want real quick. The actual graph of a cubic. X to the third power. Right, there it is. And then if I put in, let's just say I have x to the, nope, take that back, x minus 4. And then that's where I'm going to put it to the third power. Plus 5. So that one's going to shift us to the right 4 and up 5. To the right 4 and up 5. And that's what's happened. The center of the graph is now 4 units over and 5 units up from where it originated, from the parent function. Okay. And that's that. That's not too difficult. All right, let's move on. This is just going back through what we just talked about, so I'm not going to skip over those. All right, reflecting graphs. All right. And we have 2 reflecting points. We have the x-axis and the y-axis. All right, so another common type of transformation is called a reflection. For instance, when you consider the x-axis to be a mirror, the graph of h of x equals negative x squared is the mirror image, or the reflection of the graph of f of x equals x squared. So basically, if you'll notice, our parent function there is if we make that function negative, it flips it across the y-axis. Basically, across the x-axis. If I folded the x-axis, all right, it's going to lay on top of each other. Okay? It flips it the other way. If I look at this parent function, all right, the cubic, if I change this, if I clear that out and I just say the negative of x cubed, I make that function negative. Notice it flips it along. Now that one looks like it's flipping it along the y-axis, but it's actually, if you flip it heads over heels right there, flip it, it would line up perfectly with that right there. Okay, if I had, let's just go with the x squared. Negative x squared. Notice there's original, it flips it. Okay, now even if I change this, and if I have negative x squared, let me delete that. Whoops. My fingers are too big for this computer. Clear that out. If I have negative x squared, and then I add 5, okay, what that's doing is it's moving, the plus 5 is going to move it up 5 units, and the negative out in front of the x squared is going to flip it upside down. So there's the parent function. Notice it's flipped upside down and moved up 5 units. Okay, so that's what's happened when we make that negative. It puts the mirror image across the x-axis. All right, and then we're going to look at here also, what would cause a reflection across the y-axis. So notice right here, reflection across the x-axis, you just make the function value negative. So whatever the function value, the parent function is, if you put a negative out in front of it, negative x squared, negative x cubed, okay? Now, notice the difference here. If I substitute or replace the x within an equation with a negative x, that reflects it the opposite way across the y-axis, okay? Now, a lot of time, if you see like a parabola, the parent function of a parabola, it is symmetrical around the y-axis. It's not going to look like anything happens. But let's say, and let me make sure I get this right. If I have my parent function f of x equals x squared, and then I have f of x equals x squared, or x minus 3 squared, okay, we know that is going to shift that parabola, what, to the right 3 units, correct? All right, now if I put a negative out here, out in front of that, I'm changing the whole function value to negative, and it's going to flip it across the y. It's going to make it upside down. So let me just show you that. So if we have, let me clear that out. If we have negative, and then what did I have that? X minus 3. I can't remember what I wrote, but let's just say we can. All right, so this is going to be a graph that's pushed to the right 3 units. And because the negative out in front of the x, it's going to flip it down and open downward. There you go. It moved it over to the right 3 and it flipped it over downward. Now, what if we're wanting a reflection across the y-axis? Well, if I just work off the standard one, when I reflect that, because it's symmetrical to the y-axis, you're not going to be able to see. But I should be able to see here, because if I reflect that across if I reflect the red one across the y-axis, it's basically going to put the graph over here. Okay, and let me make sure. And so what it says does that is if I were to put in f of negative x, so that would be negative x minus 3 squared. All right, that should reflect it across the y-axis. So notice I'm making the x negative, and I hope I've got that right. It's been a while since I've done this. So let's see. Negative x minus 3 squared Yep, that's what happened. Now notice, when I did that, I didn't put the negative out front. So really, if I want to reflect that graph, the red graph, what I should have done is I should have inserted a negative right here. I should have left everything the same, except I made the x negative. All right, and now that graph, if you'll notice, is a reflection across the y-axis. Right? If I folded that across the y-axis, it would lay right on top of it. So a reflection basically from opening it up to opening down is when we make the entire function value negative, which is this negative out in front of the parentheses. And then what flips it to the other side of the y-axis is when I make the x, only the x negative. All right. So hopefully that makes some sense there. All right, and then here's just some examples. If you notice right here, x squared is the parent function, negative of x squared flips it down. What is this? Oh, they want us to write the equation. So what would be the equation right here? This one looks like it is from the parent function. Okay. This one looks like the vertex has been shifted up 2 units and it's been flipped over, correct? So this one would be f of x equals negative x squared, and then I would say plus 2, because that plus 2 is going to move it up the 2 units to that where the vertex is. So it got moved up 2 and then flipped over by that negative out front. Same thing here. This one's been shifted to the right 3, and that's it. Right 3 and then flipped over. So this is an example of it being negative x minus 3 squared, right? I don't know why it does that sometimes. Okay, so that's that parabola. It's been shifted to the right. That's what happens when I subtracted 3, and then I put the negative out front. That causes it to flip across the y-axis or flip upside down. And that's just explaining what we just talked about. All right, non-rigid transformations. Non-rigid transformation means you don't keep the exact same shape. All of those, you had the exact same shape of that parabola. It just got shifted around or maybe flipped. All right. This is going to talk about making maybe a parabola that's more narrow or wider. That's called a non-rigid transformation. So what we're talking about is if this were the parent parabola, forgive me, I'm a terrible drawer on this. A non-rigid one would be one that's a lot more narrow, like that right there, or one that is real wide, like that. That's a non-rigid transformation. So that's what we're going to talk about here. It causes that distortion, a change in shape of the original graph. For instance, a non-rigid transformation of the graph of y equals f of x is represented by g of x equals c. Notice what they're doing to change a non-rigid transformation is they're multiplying a number by the function value. That's what that c f of x is. They're picking a number and multiplying it by the function value. So we can do a little exploring on our own here. Let me clear out these two. So if I said 6x squared, I'm taking a number and multiplying it by that function value. Let's see what happens. That makes it more narrow. Okay. Now, what's going to make it more wider is if I can either divide or I can multiply by a smaller number. Let's say I say 0.25, or that's 1/4, right? 0.25x squared, when I graph it, notice that makes it wider. So taking and multiplying a number, on this one, multiplying by a number for a quadratic, multiplying by a number bigger than it's 1 is the dividing point there. Bigger than 1 sort of makes it more narrow. If I multiply by a number less than 1, or I divide by something, it's going to widen it out. And I would say similar to the absolute value one too. It will do sort of the same thing. It'll stretch. All right, and that's what it says right here. You get a vertical stretch when C is greater than 1, and a vertical shrink when 0 or C is in between 0 and 1. So they're talking about a vertical, which means stretching it. Like if you took the top and the bottom of the y-axis and stretched it apart, that's what would happen. It looks like it, to me, it looks more narrow or wider. Or if you put in a number less than 1, or you divide by a number, if you took the top and the bottom of the graph and squeezed them together, it would fatten everything out, and that's what's happening. All right, another non-rigid transformation of the graph is represented by h of x equals f. Notice what they did there. They took the x and multiplied it by a number. Not the whole function, just the x. Okay? And same thing, except this is a horizontal. When c is greater than 1, so if I put something like this, h of x equals, in parentheses, 3x squared, the c is greater than 1, that is going to be a horizontal stretch. And it's going to look very similar because of the way parabola is. That means if I had here, I have my normal parabola, horizontal. If I took the sides of the x-axis and pulled them apart, okay, it would stretch it out like this. Okay, so let's look at that in play up here. So it's going to be very similar to the other because of the way a parabola is set up. But if I put, let's just say 4x, and then I square that, that is a horizontal stretch. Well, I'm getting it backwards again. Did I read it wrong? Let's see, is greater 1. Oh, that's a horizontal shrink. Sorry, I read it backwards. I got to read it. That's a horizontal shrink, and that's what happened. It's like I took the sides and pushed it together, made it more narrow, which makes sense because if I simplify that down, that turns into 9x, which sort of goes back to what we were talking a minute ago. We multiply a big number out front of the x squared, and it causes it to narrow out. It's weird with a parabola because the horizontal and vertical sort of overlap each other. And then if I multiply by something less than 1, greater than 0, if I say 1/2 x squared, that is where it's going to fatten out. I'm going to stretch out the x-axis. Okay? So let's go on. I think this is all our... All right, so here they're using the absolute value function. All right, so if we start with x, all right, here they've taken and multiplied a number by that function value. So they says that is a vertical stretch when that happens. So if I multiply by a number out in front of the entire function value, that's like I'm going to take the top and the bottom of the y-axis and stretch them apart, which is going to make it look more narrow. And that's what they get right there. Oops. And actually, they did. Yep, that's it right there. This is the standard f of x, f of absolute value of x, and this is 3 times the absolute value of x. All right, then the next one is 1/3 times the value of x, so that is a value less than 1. So this is the opposite. That's if I take the top and the bottom of the y-axis, and that is a vertical shrink. So I'll push them together. It would make the v look fatter. So what it would look like, it would look more something like this. All right, once I graph this one right here, because that is shrinking down and pushing the y-axis together. All right. And that's what they're showing right there. And of course, if you forget a little bit, you can always punch it in your calculators like we've been doing and comparing it to its parent graph. And that's sort of it. We've got all our shifts. Shifts left, right, up, down, reflections, and now shrinks and stretches are all right there. And that is everything.